Welcome to The Explainer. Today we are diving into one of the most, elegant concepts in all of AI, the autoencoder. Now, this is a tool that teaches a machine how to find the very essence of data, and it does it all by itself. It might sound super complex, but the idea at its core is just brilliantly simple. And believe me, it is changing how we approach everything from generating images to detecting fraud. So let me ask you this. Imagine you've got thousands, maybe millions of photos, but with zero tags, no descriptions, nothing. How in the world could you teach an AI to understand what's in them? I don't mean just to slap a label on them, but to really grasp their fundamental essence. Well, that's exactly the kind of puzzle that autoencoders were born to solve. Okay, so to solve that puzzle, let's just strip away all the jargon for a minute. At its most basic level, you can think of an autoencoder as a really intelligent copy machine. Its main goal, its whole purpose, is to take something in and then just try to recreate it. Simple as that. Now, for the technical bit. An autoencoder is a type of neural network, and it's got two distinct parts that work together. First, you've got the encoder. Its job is to take the input, say an image, and squeeze it down, compress it into this essential little summary. Then the second part, the decoder, takes that super compact summary and tries its best to reconstruct the original image using only that core information. You know, a fantastic way to picture this is to think of an artist doing a memory sketch. The artist, that's our encoder, they look at a really complex scene. Now, there's no way they can remember every single leaf on every tree. Instead, they capture the essence in their mind. You know, the key shapes, the way the light hits, the overall feeling. Then they turn away from the scene and try to draw it from just that mental summary. That drawing, that's the work of our decoder. But wait a second, you might be thinking, what's the point of just copying something? Isn't that a waste of time? And that is a totally fair question. The answer is where the real magic happens. See, the genius of an autoencoder isn't in making a perfect copy. It's all about a clever constraint we build right into the middle of the whole process. Look, if the goal was just a pixel for pixel perfect replica, the network wouldn't learn a thing. It would just be a fancy, expensive photocopier. The real learning, the good stuff, it happens in the struggle to reconstruct the original from that compressed summary. By forcing it to do this, we're actually forcing it to decide what information is truly important enough to keep. And that constraint has a name. It's called the bottleneck. We deliberately design this middle layer to be tiny, forcing all the rich information from the input through this narrow little opening. It's an information squeeze. And it means the network literally can't afford to remember trivial details. It has to learn how to identify and encode only the most essential, defining features of the data. This visual here just lays out the whole journey perfectly. Data comes in at full size. It gets squished down by the encoder layers until it hits that tiny bottleneck. That compressed code is what we call the latent representation. It's basically the machine's abstract idea of the input. And from that tiny code alone, the decoder then tries to rebuild the original, expanding the layers back out again. Now, maybe the most remarkable part of all of this is how it learns. This is a type of unsupervised learning. We don't need to give it any labels, no cat, no dog. The input image is its own answer key. The network has one goal: minimize something called reconstruction loss. In plain English, that just means make the output look as much like the input as you possibly can. This self-correcting loop is what makes autoencoders so incredibly powerful when you've just got mountains of unlabeled data. That basic design, that's just the starting point. Researchers have come up with a whole family of specialized autoencoders, each one with its own unique twist, designed to solve a very specific problem. Let's take a look at a few of the big ones. So, for instance, a denoising autoencoder is a bit of a tough teacher. It's intentionally fed corrupted data, like a really grainy photo, and its goal is to reconstruct the clean version. Then you've got the sparse autoencoder, which adds another constraint:
forcing the network to only use a few neurons for its summary. This makes it amazing at finding really distinctive features. And of course, the most famous of all might be the Variational Autoencoder, or VAE. It learns the underlying patterns so well it can actually generate brand new, completely original data that looks just like what it was trained on.
Okay, this is all fascinating in theory, but where does this tech actually show up in the real world? Well, the applications of autoencoders are all around us, often in places you'd never expect. Yeah, image processing is the most obvious place to start. Because they learn the essence of what a clean image looks like, they can take a grainy photo and denoise it, or even fill in missing pieces of an old picture. They're also used for really smart compression, where that latent representation becomes a super efficient way to store the image. They can even do super resolution, which is basically dreaming up the details to turn a low-res photo into a sharp, high-res one. Now this is one of my favorite applications, anomaly detection. The logic is just so simple and brilliant. You train an autoencoder on nothing but normal data. Let's say millions of totally legitimate credit card transactions. It gets really, really good at reconstructing them. But then a fraudulent transaction comes along. It's so different, so weird, that the autoencoder completely botches the reconstruction job. That huge spike in error, that's the alarm bell. It's a massive red flag that something is very wrong.
And it's not just about pictures, not by a long shot. In natural language processing, they can boil down an entire document to its core meaning. Recommender systems use them to create a sort of taste profile for each user, which leads to spookily accurate recommendations. And in healthcare, they can analyze medical scans, learning what normal tissue looks like so they can flag subtle abnormalities a human doctor might miss.
So it's pretty clear that autoencoders are an incredibly powerful and versatile tool. But like with any technology, it's really important to have a balanced view, to look at both their amazing strengths and the challenges that we're still working on.
So, on the one hand, the biggest advantage is obvious. They learn powerful features from raw data without needing any human labeling. That's huge. But that power comes with some hurdles. If you're not careful, they might just learn a cheap shortcut to copy the input without really understanding it. And that compressed latent space, while powerful, can be a bit of a black box. It can be really hard to figure out exactly what the AI has decided is important. And that really leaves us with a final, pretty fascinating thought. When you get right down to it, an autoencoder is a tool for deciding what's important. So as these systems get better and better at summarizing our world, our art, our conversations, our science, it raises a profound question. What essential details will AI choose to remember about us? And what will it decide to just forget?